Um, Welcome. Good morning. Thank you all for coming. There was a little bit of a room switcheroo, so this talk is thinking in Ecto. If you're looking for the macros talk, it's across the hall. It's where I would be if I weren't talking right now. So if you feel like that's where you need to be and you want to walk over there, I will not be offended. It's all right. So Ecto. Ecto is a database library for Elixir, and it ships by default with Phoenix. So there's a pretty good chance you'll run into it at some point. And in this talk, I'm going to talk about some of the high-level concepts that I think are helpful as you're starting to wrap your head around the way Ecto works. These are the big ideas underlying Ecto's design, at least from my perspective. Now, I should clarify that when I say big ideas, I'm not necessarily talking about original ideas or groundbreaking ideas, ideas you've never heard before. Depending on your perspective, you may not even think these are good ideas. But these are, in my mind, the ideas that make Ecto Ecto. And if you keep them in mind as you're starting to explore the API, hopefully things will start to make a little more sense a little more quickly than not. Now, I won't just live in the world of highfalutin, high-level concepts the whole time. I'll be illustrating with some actual code. And if you're brand new to Ecto, you've never seen a line of Ecto in your life, or even if you have, you may not grok every single line in the presentation. That's okay. Mostly what I'm hoping you'll take away are some higher level concepts, and if every single line of code doesn't make sense, hopefully it will once you actually start working with it. So let's start with big idea number one, the repository pattern. So Ecto follows the repository pattern for data access. This might not be one that you've run into. With the prevalence of object-oriented languages for the last several years or decades, the active record pattern has become more popular for database libraries. It shows up quite a lot. The repository pattern is perhaps less well known. But if you've been working in active record for a long time and you're switching to Ecto, this is the first thing that will start to mess with your head. So the active record pattern sort of breaks down like this. And by the way, when I say the active record pattern, I'm talking about the general purpose pattern of data access that is called active record, not specifically the active record library that ships with Rails, which is based on the active record pattern. Does that make sense? Okay, because I kind of forgot what I just said. Here's how the active record pattern kind of manifests. Let's say we're building an app that is going to be a music database. It'll track our music collections. So we'll have artists, albums, tracks, and whatnot. We might fetch an artist with something like this. We have our artist class, or whatever it happens to be. We give it an ID. We get a record back. We change that record in memory. And then we save it back to the database. Now, this makes a lot of sense for object-oriented languages because, of course, objects have behavior. It makes a little less sense for functional languages because data and behavior are separate. The repository pattern has a different take. The central idea is that there is some piece of code in your application, a module, a class, an object, whatever it happens to be, and it alone knows how to talk to the database. And so the rest of your application queues up operations and hands them off to the repository. And the repository sends it across the wire to the database. Simply put, if you want to talk to the database, you talk to the repository. And here's how it plays out in Ecto, same scenario. So we have our repository module, which by convention is usually called repo. We call get. We have an artist schema, which we'll talk about in a minute. Give it an ID. Now, if we want to change it, there are a couple ways to do it, but one typical way to do it is to use the Changeset struct to create a change set that models the change that we want to make. So in this case, we're changing the name. And then we update again by handing this change set off to the repo for fulfillment. So if you look at these two side by side, so there's active record on the left, there's the repository on the right. One thing you notice is that in active record, the communication with the database is a little bit hidden. Unless you really know the API, you wouldn't necessarily know that that call there is sending some data across the wire. Whereas with Ecto, basically anytime you see the word repo, you're talking to the database. So you can scan very quickly through the code and see exactly what's going on and when it's going on. That brings us to big idea number two. explicitness. So just like the Elixir language itself, Ecto favors explicitness and likes explicit behavior over implicit. As a general rule, Ecto does not make a lot of decisions on your behalf. That's not a strict rule, as a general rule. But for the most part, it wants you to spell things out for it. First place you run into this, by the way, the podium is wobbly, but doesn't seem to be tipping over anytime soon. So every now and then I see eyebrows going. I think you're all perfectly safe. But if you want to move to the back, that's okay. The first place you run into this is schema definitions. So in Ecto, schemas are maps between your database tables and structs in your Elixir code. Now, some libraries will figure this out for you. They will introspect the database, see what the fields are in each table, and create some data structures for you to work with without you having to do anything. Ecto makes you spell it out, and it looks like this. So if we want to create a struct for our albums table, we create a module called album. We call use Ecto schema to pull in the critical functionality, and then we iterate through each of the fields. So we call schema, provide the table name, which in this case is albums, and create a field for the title, which is a string, and a field for the release date, which is a date. And then there's a convenience function called timestamps, which gives us created at and updated at. Now, once we've done that, we have this struct available to us, just as if we had called def struct using regular old Elixir. But this is a little bit special because it's got metadata that helps connect it to our albums table. Now, this might seem like unnecessary work. Why should you have to spell out all the fields in your schema when you know there are tools that out there will do it for you? Well, this gives us some flexibility, which we'll see how that works a little bit later. Now, the next place that explicitness can kind of bite you a little bit is working with associations. So Ecto supports this notion of associations, creating connections between different database tables and their associated structs. So we just defined an album struct. Kind of makes sense that we would have tracks as well. So here's the schema for tracks. There's a title, which is a string. The duration, that's the length of the track. We'll save that as an integer, the number of seconds. And then an index that indicates where in the album it is, track 1, track 2, track 3, or whatever. Now, we can connect the tracks to the album with the belongs to call. So we're saying that a track record is always going to belong to some album, and here's the name of the module where that's defined. It assumes that in the database you have a foreign key called album ID, but if your foreign key is named something else, you can supply it. And then in our albums schema, we can make the association the other way by saying this album has many tracks, and again, we supply the module name. Now, how you use these associations is where you kind of need to be careful. So let's say we've fetched an album, and now we want to look at the tracks. Intuitively, you would just say, oh, I know, I just do album.tracks. But what you're actually going to get is this, the dreaded Ecto association not loaded. Now, this is a placeholder value that tells us that the associated tracks for this album haven't been loaded yet. Loading associated tables, associated records from another table involves another round trip to the database. We didn't tell Ecto to do that, so it's not going to do that for us. Some libraries will do this for you. If you made this call, they would say, oh, look, they asked for the tracks. We don't have them. I will go get them, and then run to the database behind the scenes and bring the tracks toward you. This is a feature called lazy loading. It's very handy. It's very nice. It saves you some typing, but there's a problem. And it goes a little something like this. Let's say we grab a whole bunch of albums, everything in our database, and we want to iterate through them one by one. And now we want to iterate through the tracks of each album. Let's assume for a moment this worked. In Ecto, this won't work, but we'll assume for a moment that it did. Each time we hit that particular line, we have to make another round trip to the database. So we've got one album, go get the tracks. Next time through, we've got a new album, get the tracks, over and over again. That's not a problem if you've got 50 albums. If you've got 5,000 albums, it's a very big problem indeed, and it's got a name, the n+1 query problem. So named because n is the number of queries you have here. In this case, it's the number of albums. plus 1, which is the album record that we did at the beginning. This is a particularly nasty problem because this one sneaks up on you. You won't run into it in development when you've got just a few records. Your app will handle it fine. It won't happen in the early days of production when you've got a few customers, because again, it'll handle it just fine. The day it's going to hit you is the day that your viral campaign succeeds, and suddenly you've got untold numbers of new users adding untold numbers of new records, and suddenly at 9 p.m. on a Saturday night, your app slows to a crawl and you don't know why because you didn't change any code. But guess what? Your database changed. So Ecto's solution to this problem is it does not support lazy loading at all. When you want to load associated records, you got to ask for it. There's two ways to do it. You can pipe your results to the repo preload function and say what the association is. Or if you're using the query syntax, which we'll talk about in a second, you can supply preload as an option, and it'll do it for you. In either case, this will then work. So this is a little more typing, yes. But in exchange for a little more typing, you could potentially save some grief down the road. All this explicitness we just talked about actually is there for your benefit. Eat your vegetables, kids. Big idea number 3, operations as data structures. This sounds a little abstract. Think back to the active record pattern that we looked at earlier. In that case, we made changes to the database by manipulating the in-memory representation we had of that record and then shooting it back to the database. So these objects that represent database records are the primary data structures that we work with. Now in Ecto, we certainly do work with our schema modules and the structs that we've created, the artist, the album, the tracks, what have you. But the real action happens in data structures that model operations on those records. One of those is query, which we use to pull records from the database. Another one is Changeset, which we use to update records to the database. And then multi, for when we need to do more than one thing at the same time. Let's start with query. So Ecto uses macros to create a DSL for writing queries that feels a lot like SQL itself. And I mean that in a good way. Here's a SQL query that fetches all of the albums by Miles Davis. So we select from albums, we join on artists, then look at the artist name. Here's that same query in Ecto. As you can see, a lot of the keywords the same and the structure is kind of the same. So if you're familiar with SQL, writing queries in Ecto will feel pretty familiar. Now at this point, the query is just a data structure, nothing more. It hasn't fetched anything. No databases have been harmed in the making of this query. Nothing happens, again, until we hand it off to repo, and then it gets fulfilled. Now, because it's a data structure, that means that we can manipulate it and change it and build on it before we send it off to the database. And that's possible because when we call the from macro to kick off a query, we can provide the schema module, we can provide the table name as a raw string if we want, or we can provide another query, in which case everything that we got from the first query will go into the second query and we can refine it. So if we take our query that we had before, fetching the albums of Miles Davis, we can then create a new query, and we say from a in query, our previous one, and now we're going to add some more parameters to it. We're going to filter further by looking for all of the albums that have tracks that are longer than 10 minutes. We're looking for the self-indulgent albums by Miles Davis. Now from here, you can see that it's pretty easy to make these queries a little more general purpose by putting them into functions. So taking this first query, we could create a function that takes the name as a parameter and then generates a query for any artist. Similarly, we could take the second half of the query, parameterize the duration, and put that into a function. And the benefit of that is that we have these nice functions that give us building blocks that allow us to build up queries like this. They make them nice and readable. So breaking up queries into smaller pieces that get reused and put them together is a nice feature of the query data structure. Second big one is Changeset. So Changeset is a struct and a module that handles the entire life cycle of database updates. And it's kind of in 3 main phases. First is filtering and casting. So we take a bunch of input from somewhere, a form submitted by the user, an API call, whatever it happens to be, put them into the change set. Then we do validations to make sure everything is okay. And then we actually hand the change set off to repo for fulfillment, and then we get a change set back if there were any errors. And that change set we get back has all the changes we made, plus any error information that went along with it. So the whole thing gets wrapped up in the change set. And in code, it sort of looks like this. We import the change set. We've got our params that came from somewhere. We're creating a new track here, so we've got a title, we've got an index and a duration, and some other nonsense we were maybe using for JavaScript, who knows. We create a change set by kicking it off with the struct we want to use. We call cast, and we supply the params that we got from the user, and we supply a list of the fields that we're interested in. So we're saying, okay, from these params, we want title, index, duration, anything else, just throw it out, we don't care. So at that point, the foo value is gone. And now we can validate it. And the change set module provides a bunch of handy validation functions that do most of what you want, but you can always write a custom one yourself. And then we see if it works. We hand it off to repo to insert, and we get a tuple back. If it's okay, that means everything worked. If we get an error, then again, we'll get the change set back, and it'll have the errors for us. Now, the interesting thing about this arrangement is that validations are part of the change set struct. They're not part of the schema. When we set up the schema, we didn't say these are all the things that make a valid track record. We put that off until this point where we're actually making changes. And this is because validation requirements can change depending on how you're updating. Think about tracks for a second. In the real world, some tracks are parts of albums, and some tracks are just singles that are released separately from an album. So based on that, we could create two different change set functions. Well, we could create a change set function that pattern matches on the params that we got from the user. If there was an album ID in there, we can say, all right, this one's part of an album. Let's make sure that the album ID is valid. Let's make sure the index was supplied and that it's greater than 0. But if the params didn't have an album ID, we can say, okay, this one is just a single. We don't need to worry about the album information. Just say the title. So this allows for a much more granular approach to validation and can be really beneficial, especially if you have different contexts in which you're saving things. So the last data structure I want to talk about is multi. This is kind of a new one. I think it came in Ecto 2. And this is for when you need to do more than one operation at the same time. So here we've got a change set that's going to make some edits to an album record. It's all ready to go. We're about ready to hand it off to the database. But let's say that as part of this application, we want to track the edits that are made to the database, and we want to credit the user that made them, sort of Wikipedia style. So in addition to updating the album, we want to update the user record somehow and bump up their contribution count. We want both of these operations to succeed or to fail and the database to be rolled back. We wouldn't want the album change set to succeed and the user not get credit for it. So the easiest way to do that is with a transaction. And this is sort of like a database transaction. We call update bang on the album change set. We call update bang on the user change set. If either one of them fails, we go back to where we were as if nothing ever happened. In simple cases, this works great. And if this is all you need to do, transaction is fine. But you may want to take slightly different action depending on which of these transactions fails. At the very least, you might want to just write something out to the console that says the album change set failed or the user change set failed. That's pretty simple. Even if you want to do just that, your code's going to look like this. You've got to run the first change set, see if that worked. If it didn't, put an error. If it did, try the second change set, see if that worked. And already this is like no fun to read on a slide in a presentation. Multi can help us out with this. So using those same two change sets, instead of going straight to a transaction, we'll create a multi with the new command, new function. And then we start piping it into operations that we want to queue up. So we want to say, all right, we want to run an update operation. You got to give it a name. Each part of the multi needs to have a unique name. So we'll use album for this one, and we say the album change set. We do the same thing for the user change set. We call this one user. We give it the user change set, and we're ready to go. Now again, at this point, it's just a data structure. Nothing has happened in the database yet. Once we're ready to go, we hand that off to repo transaction. So transaction can take an anonymous function like we saw before, or it can take a multi, and we can capture the result. Now once we have the result, we can pattern match on it to find out what happened. If the first tuple is okay, that means everything went through and all is right with the world. But if the first part of the tuple is error, we can then look at the second part of the tuple to see which one croaked. That's what these original names are for. So in that first arrow clause, we can see that the album change set failed, so we'll print that out, or the user change set failed. So already, this cleans things up considerably. It gets better. You're not restricted to just database operations as part of a multi. You can actually run any arbitrary piece of code in it. Let's say that we went a little further with our user tracking, and once they reached a certain threshold, we might want to award them a badge and send them an email saying, thanks for being an awesome user. We love you. This might get all wrapped up in a function here, which we call check user progress. We can execute this function as part of the multi using the run function. So now we have the same thing we did before, but now we're saying, okay, if those updates succeed, then execute this function. And we use the capture operator there to indicate it. And another nice thing about multis is they're very easy to test. There's a toList function that will spit out a data structure that represents all the operations that you have queued up. So one of the nice things about being a data structure is that you can compose it with different pieces that get reused. Like we could take that whole user tracking and updating and sending an email part, move it off to a separate service module that gets reused throughout the application. As you start putting those pieces together, you want to make sure that your code is assembling the pieces correctly. So you can introspect on a multi, make sure everything is lined up the way you expect without actually having to send it to the database. And that can speed up your tests quite a bit. So the important data structures: query, change set, multi. Get to know those. That's where you'll be spending a lot of time. Big idea number 4, flexible schemas. Now earlier, at the very beginning, I mentioned that doing the hard work of mapping your schemas to your database table by hand would open up some options for you. So we'll take a look at those now. Schemas in Ecto are very, very flexible, and you can set them up to do exactly what you need. First thing to know about schemas is you don't actually need them if you don't want them. Here's a query that fetches an artist of Miles Davis. You could rewrite this query like this. Instead of using the schema module in the first part of the query, you can provide the table name as a string. The only difference is now you have to provide a select option to say which fields you want back. One of the benefits of working with schemas is that Ecto will always fetch whatever fields you've defined in the schema when it does a query and pulls some records back. If you're bypassing using schemas, you have to be specific about it. And the result set will be slightly different each time. In the first query, you'll get an artist struct back. In the second instance, you'll get a list of maps where each map represents a record that came back, and the keys in the map are the columns that you asked for in the select. And why would you want to do this? Well, some queries don't really benefit from having schema. Think about reporting queries, where you're gathering up a lot of statistics. Like in this particular case, all we want are the names of all the artists in our database and the number of albums that they've created that we have access to. Now, that doesn't really sound like any schema that we've defined. We've got the artist name, sure, but we're not interested in any of the other artist properties. And the number of albums is just a count. That's not something that's being persisted. So we can write the whole query without the schema and get back exactly what we want, which is just the artist name and the number of albums, sorry. Schemas are supposed to make your life easier. So if you're writing a query and you're finding yourself tripping over which schema should go where, consider rewriting it without schemas. It might be easier, and you have that option. The next thing to know about schemas is that we can bend them slightly when the need arises. So think for a moment how we tend to work with our databases. In the early days, we start to figure out what our data is. And because database tables can be kind of unforgiving, we kind of start there, and we design our database tables. Now we usually want some kind of representation of those records in our application code. So we kind of end up usually creating data structures that pretty much mirror our database tables, particularly if it's done for us automatically. And then a lot of our tools tend to make it easiest to use those same data structures down in our view layer. For example, Phoenix forms work perfectly with Changesets, thanks to the Phoenix Ecto package, which bridges the gap. You can hand a Changeset off to Phoenix form and you've got lots of nice convenience functions. So just kind of by inertia, it ends up being easiest to create forms that end up looking sort of more or less like our database tables. However, I don't think database schema definitions have ever won any design awards. The alternative is to do a bunch of coding by hand, but no one wants to do that. So what are the alternatives? Well, Ecto gives us some alternatives. Think back to our tracks schema. Now this duration field is a little bit problematic. We want to store it as an integer representing the number of seconds, but that's almost never the way we see it in the real world. When you see a track listing, it's usually expressed as minutes and seconds, as a string. So nobody wants to deal with 205. What we usually see is 325. If we wanted to present this field as an integer field to the user, they would have to do math. And I think we all know that's not going to end well. But at the same time, schemas and change working with something like Phoenix forms, we don't want to lose that. So Ecto has an out. We can add another, we're going to tweak this schema slightly. We're going to add another field called duration string. This will hold the duration as a string the way the user sees it, 325. Now we also added the keyword virtual true. This is our clue to Ecto saying, I'm just using this for my own purposes. Don't try to persist this anywhere. Don't try to look for it in the albums table. You won't find it. Or the tracks table, I'm sorry. Now, once we've got that set up, we can present duration string as a form element to the user and create a change set just like we normally would. We take the title, take the index, we've got the duration string, we do some basic validations. And now we're going to do a custom transformation. We're going to convert that duration string to an integer. And the function might look something like this. We take our change set, we pull out the duration as a string using getField, and then we take that and we convert it into an integer. So we take the 325 that the user gave us and we turn it into 205. How you actually do that, I leave to your imagination. And then we call putChange to take our new value, stick it back into the change set, but this time with the actual real value we're going to save, duration. And then back here, once we've done that, we can validate it to make sure it's all okay, and then send it off to repo, and we're good, and no one's the wiser. So we were able to adjust our schema slightly to make a better UI for the user, but without losing all the advantages of using schemas and change sets together. We can go even further in this direction. What if I told you that schemas don't actually need database tables at all? If you read this documentation for schema, at the top it says schemas can be used to map any data source. And somebody went to the trouble of italicizing any. So I think they mean it. In that last example, we were able to tweak the schema slightly to make it work better for a user interface. But some models are a little bit more problematic than others. Think about artists. Artists are kind of tricky to model because in the real world, they sort of fall into two categories. On the one hand, you've got bands, the Beatles, Depeche Mode, the Shags, and the like. But you've also got solo artists who sound more like people. Taylor Swift, Joan Jett, William Shatner, all your favorites. And they have slightly similar properties, but not quite exactly the same. And in a perfect world, this is how we'd present it to the user. If it's a solo artist, we'd give them 3 name fields, so we can cover Sia as well as John Cougar Mellencamp, and a birth date and a death date. But if it's a band, we just need 1 name field, and bands don't really have a start date or an end date. It's more like years active, so we'd want to present it that way. Now, in the world of relational databases, it doesn't really make sense to have 2 separate tables here. Because basically, fundamentally, at an abstract level, these are entities that produce albums, and that's what we're interested in. But real life is not quite so hard. So how can we bridge this gap? So first, we'll make a schema for the artist table. This is the one that will actually map to the database. So we've got 3 name fields, and we'll use start date and end date. Now, it would be pretty indecorous to prompt a user for the name of their or for their artist's start date, or even worse, for their end date. That's not okay. But in the cold, hard, abstract world of databases, it's absolutely fine. But now we're going to create a second schema. And this will be our solo artist schema. And this will look more like how we want a solo artist to look. First name, middle name, last name, birth date, and a death date. Now notice in this case, we didn't call schema, we called embedded schema. So just like in the last example, setting that field to virtual was our tip-off to Ecto that this is not really getting persisted anywhere. Same thing here. We're saying that this schema is not going into a database anywhere. It's just a map that we're setting up for ourselves. Similarly, we make a band schema. And this one has simpler fields, just a name, a year started, and a year ended. So how do we work with these? So let's look at how we'd insert a band. We'd create a Changeset function, as we normally do, that takes the parameters, we cast them, we validate them, we make sure the years are okay, make sure the year ended is not before the year started, or something like that, just as if it were a first-class citizen in Ecto world. But we add another function called toArtist. And this takes a band struct and returns an actual artist struct that we'll save. So we take the band name, we put it in the name1 field, and for start date, we create a date based on the year the band started and call it January 1st. And for the end date, we take the year that they ended and December 31st. That's a reasonable compromise. And to insert a new one of these, we generate the change set with the params, just like we normally do. Check to see if the change set is valid. If it is, we can call apply changes on the change set. And what this will do is spit back the underlying band struct that's in the change set, but with all of the changes that the user supplied applied to that struct. So it's as if we had saved it to the database, but without actually saving it to the database. Then we convert it to an artist record using our toArtist. And now, finally, we hand that off to repo. So the flexibility of schemas allows us to break up this juggernaut and this tendency for our database tables to become our UI. We can have all the benefits that come with working with schemas and change sets and how it's easy to work with in certain form and view libraries, but we can shape our UIs the way that we want and still make it easy to save it back to the database without a lot of extra coding. Thank you. Ecto gives us these options. And that brings us to the last one. Think of Ecto as a set of tools and not so much a framework. All the different pieces of Ecto work together really nicely, but how you use them is kind of up to you. You can use schemas for all of your database records, or don't. Skip it altogether. You can use change sets to do updates, or you can go kind of low level and use the update all function in repo to manage those changes a little more manually. You can keep the bits that you want and throw out the rest. Because not all projects are created the same, and not all databases are created the same. And the way you use Ecto on one project might be very different than the way you use it on another project. It's got the power and the flexibility behind it so that you can craft the approach that you want. There's no one right answer. So, 5 big ideas I hope you'll take away with you. The repository pattern, explicitness, operations as data structures, flexible schemas, and again, always think of it as a set of tools. Before I wrap, I want to say a couple of thanks. First to my colleague, Daniel Berkampus, who's a screencast on Elixir and Phoenix, and his blog post really helped me get a good handle on this stuff. And to Eric Meadows-Johnson, not just for creating Ecto in the first place, but for helping answer a lot of my stupid questions. And speaking of Eric, he and I are collaborating on a book together called Programming Ecto. It's coming soon from Pragmatic Bookshelf. It hasn't been officially announced yet. It was supposed to be sometime this week, so y'all are getting the inside scoop. But you can follow me, and I'm sure I won't be shutting up about it once it's released. So I'd like to thank you all for coming. I'm Darin Wilson. I'm the web team lead at Infinite Red. We specialize in web development in Elixir and mobile development with React Native. So if you're interested in any of those things, feel free to talk to us. There's a gaggle of us here at the conference. And I'm just about out of time, but I'll be hanging around afterwards, so you can ask me questions then. Feel free to grab me at the conference at any time. And afterwards, you can find me at the internet here. And that URL there is for our Infinite Red community Slack. And we've got an Elixir channel in there, so that's a good place to find me as well. So I hope this was helpful. Hope you have fun playing with Ecto. Thanks again for coming, and enjoy the rest of the conference. Thank you.